So now individual waves travel in space. Okay, you have a wave pattern that moves in space, and this is what we call the phase speed. Okay, it has nothing to do with currents or flows in the ocean. This one is the speed at which the shape of the sea surface travels in space. Okay, and it can always be expressed for any wave. Sorry, for any wave it can be calculated from the ratio of wavelength and wave period. All right, so it's almost like a live video here, but I have to cough and I apologize for it. Okay, but let's continue. So now for long surface gravity waves such as tides, okay, you get a special phase speed relationship. And what are long waves? Long waves are the waves, gravity waves, which have a wavelength that exceeds the water depth by far, say more than 20 times. So if the water depth is 10 meters, if you have a wavelength of longer than 200 meters, yay, that is a long surface gravity wave. And this wave behaves like this one here. Square root g times h. Wow. So you can, if you know the water depth, work out the phase speed. Okay, the phase speed only depends on the water depth. G is a constant, it's acceleration due to gravity. It's 9.81 meter per square second. Now, in the next step, you can actually combine these two equations. You have two equations for C, here one at the top, one at the bottom. You can put them together, and what you work out is that the wave length is related to the wave period, and you have a constant or a constant water depth that relates these two to each other. Square root g times h. And this relationship is very significant for tides. Okay? Because in the open ocean, tides have a very long wavelength. Enormous, several thousand kilometers. Okay? Huge. The period is given of tides. Okay, we talk about tidal constituents on the next slide. The period is always the same, but now imagine that the tides approach shallower water. Okay, so what happens here in this equation, the h on the right-hand side becomes smaller, and this implies that the wavelength becomes shorter. So as tides approach shallower water, the wavelength shrinks and actually fits into the length of an estuary. Okay, if the estuary is long enough, like the example that I showed you, you could actually see in Chesapeake Bay that the wavelength fits into the length of that estuary. You can see a shape of a full wavelength. So this is the key in the understanding of why you can have tides. Okay, such a tides on very, very small scales. And we come back to the question of why can the tides actually be much stronger also in estuaries compared to the open ocean. Okay, so this is an important bit. Sorry for the coughing, but I think you get the key message, all right?